Hello everyone, my name is Stephen Gigrich, and this is Lab 3, Bar Magnets. As an overview of my lab report, I will first introduce the lab and the physical principles behind it, as well as go over my lab setup. Then I will go over my lab procedures, observations, and calculations. I will then show you my GlowScript simulation and outputs, and I'll end it off by answering the two questions of the main ideas of the lab. Introduction. Background information and physical principles. Vectors are widely used in physics to convey multi-dimensional information and consist of a magnitude and direction of a quantity. The Biot-Savart law states that the magnetic field strength is proportional to a constant mu naught over 4 pi, which is equal to 10 to the negative 7, the cross product of a moving charged particle and the observation location, and inversely squared by the distance. The magnetic field theory states that charged particles in motion emit fields into space that can exert forces on ferromagnetic objects. Superposition is the property that multiple fields can be added together to form a net field. Derivations of equations and formulas. In order to linearize a function, you must do the opposite operation to both sides. In this case, the opposite of an exponential function is a logarithmic function, so we take the natural log of both sides in order to get valuable information when graphing. Ln x becomes the y-intercept and n becomes the slope. The purpose of the bar magnet lab was to increase our understanding of the shape and form of magnetic fields, learn more about the relationship of their strength to their distance, and compare a computer model with real-world data. We also got more practice with GlowScript, Excel, and the array of sensors present in most modern phones. Here's a picture of my lab setup during the experiment. You can see my tape showing where the magnetometer is in my phone and the measuring tape I used. Here's the provided spreadsheet filled in with the data I gathered. From the linearization of the data, you can see that the slope is negative 2.2741, which is pretty close to being inversely squared, and the y-intercept is negative 13.815. You can stop and take a look at the data here if you want to. Here are the systems and surroundings of my lab. The system of the experiment was the magnetic field produced by the supplied bar magnet, and the surroundings of the lab were the natural magnetic field produced by the Earth. Here's a preview of my experimental results. The strength of the magnetic field falls off according to the inverse square law. Relatively, the magnetic field of the Earth is extremely weak, and magnets are fun to play around with. Lab procedures and results. Here are the steps I took when conducting the lab. I first acquired a bar magnet, tape, and 2 rulers, and downloading the magnetome map on my iPhone. I aligned my phone with the north-south axis by making Bx equal to 0, and I determined the location of the phone's magnetometer by going across the 2 axes of the phone and seeing where the strength is the greatest. I then gathered the data at the 20, 70, 120, 170, and 220 microtesla marks and measured and recorded the distance. I inputted the data into the spreadsheet and I determined mu. Some observations I had during the lab was that compared to the magnetic field of the entire dynamo of the Earth, bar magnets are extremely strong. On the microtesla scale, the distances on the centimeter scale are very sensitive, and the strength of the magnetic field decreases in strength over the square of the distance. To answer the 4 observation questions, number 1 is true when the phone is aligned with the north-south axis. Number 2 is not necessarily true, as it could be false depending on the direction and rotation of the magnet that could increase or decrease the x component of the magnetic field. Number 3 is also not necessarily true, as it again depends on the position and rotation of the magnetometer, as it could lose some of the x direction into the y or z directions. And number 4 is false as it also depends on the direction/rotation of the magnet, which could either increase or decrease the x component. Here are some of my calculations. From the linearized graph's slope and y-intercept, we can determine the n and k values of b equals kr to the n. Setting the Biot-Savart law equal to kr to the n, solving for mu, and substituting in our known values, we get the value of u to be 69.35 amperes per meter squared. Some possible sources of error on the lab include faulty magnetometer, faulty software, inconsistent magnets, influence of outside fields, and misreading of the screen or the ruler. GlowScript program results. Here's the function I used to calculate the magnetic field vectors from a dipole given a mu and an observation location. Here's the output of my code where the orange vectors are parallel or on axis and the smaller sine vectors are perpendicular. You can see how the orange vectors are twice the length of the sine vectors, which matches our dipole equations. The purple vector arrows represent the off-axis observation locations, separated at 45-degree intervals. Note the direction of these diagonals. Here's more of the code output detailing all of the vectors of the observation locations. You can stop here and look at it if you want to. Comparing my computed value versus the measure value, we see that the GlowScript program calculated the net magnetic field to be 1.746 times 10 to the negative 3 teslas, while I measured using my magnetometer the magnetic field to be 4.55783 times 10 to the negative 5 teslas. This percent error is 3,720%. I think I got this much error from a miscalculation of my mu, but I never figured out where I went wrong. Questions and answers. Here are some assumptions I had during the lab. I assumed that the strength of the bar magnet did not decrease over time, the phone's magnetometers were accurate, the software was accurate, and that there were no outside magnetic fields aside from the Earth and the bar magnet. If the BX direction was not centered on 0, then it would have had to have been taken into account throughout the rest of the experiment. It would have involved some annoying trig and would have made the calculations a lot more messy. Finally, answering the other what if question, if you were to stick two identical magnets together end to end, then I would expect the magnetic field to increase by a factor of between 2 and 1.5. The reason it's not a direct doubling is because the second magnet would be farther away than the first magnet, and the strength of that magnet would fall off to the square of the distance.